And so this next video will be focused on dilutions and how they're involved in solution prep. And dilutions are something you should be familiar with, although I'll probably point out one aspect that may never have explicitly been taught to you. But for now, let's just write what a dilution is. It's just making a solution less concentrated. And let's quickly revisit the lab. So now I'm going to dilute this Coca-Cola, and I'm going to do it with this volumetric pipette. Much like the volumetric flask, it has one line, and that line is going to give me a very accurate delivery of, in this case, 5 milliliters. And so the pipette defines my initial volume of the solution that we're making, my pre-dilution volume. Again, in this case, it's going to be 5 milliliters once I get to that line. And then I would put this 5 milliliters into the volumetric flask. And then I'm going to dilute up to that line of the flask, which will get me to a solution of 50 milliliters. And we should all just intuitively know what's going to happen to this brown color, right? As I add water, I will dilute the solution and the brown color will fade. And so let's just confirm what we already know is going to happen. Now it's not fading because the brown chemicals are reacting with the water and being annihilated. We're not actually causing any real reaction. We're just dispersing the chemicals that give it the brown color, having them spread throughout this solution. And this is going to be a very important point for later in the semester when we talk about the difference between a dilution and the equivalence point. And so there we have it, a much lighter brown than the original drink, right? And that, again, makes sense because we've diluted the chemicals inside this. And now it's ready to go. And so now let's look at the math involved in these dilutions, and I'll go through this visual really quick and then we'll make some notes. And so first of all, I'm using beakers, even though I just went over how volumetric flasks are important, but beakers are a lot easier to draw in PowerPoint, so that's what we're seeing. But we would not use beakers for accurate dilutions. But anyways, 5 moles of NaCl are dissolved in H2O to make 10 liters of solution. What is the molarity of the solution, and what will it change to if another 10 liters of water are added? In other words, if it's diluted. So molarity should be straightforward. You just take that 5 moles and divide by 10 liters. We get 0.5 moles per liter. Cool. Then we add 10 liters of H2O. As specified in the video, we have not caused any reaction. We still have the same amount of NaCl, 5 moles. It's just that they're now spread out further apart from each other in this larger volume. The new molarity would just be 5 divided by 20, which equals 0.25. Makes sense. If the volume or space has doubled, then the concentration has halved. And so this brings us to the formula that should be burned in your brain, which is the dilution formula. But let's write it down. So it's M1V1 equals M2V2. But why does that formula work? This is what's not really explicitly taught typically in Gen Chem courses. Let's start with just the M1V1, which in this problem we know is 0.5 moles per liter. And our first volume is 10 liters, and we can see that when we multiply those two together, we will get moles, specifically moles of the solute, which we identified earlier as not changing through a dilution process, which is, again, a very important point for later in this semester. Well, because those moles aren't changing, we know that this number here must also equal the second concentration and second volume that we end with. And so we can complete this triangle and see that M1V1 must equal M2V2. And it's all based on the idea that the moles of solute never change throughout the course of a dilution. Again, very important point. Now let's talk about how dilutions are involved in prep work. So let's say we have a liter of aqueous solution containing 0.20 moles of NaCl. A 100 milliliter aliquot, in other words a portion, is removed and diluted to 5 liters. So two different things are happening here. Here's our starting solution, and then we take a 100 milliliter portion of it. In other words, we're taking 10% of the original solution. And we're not just taking 10% of the volume, we wind up taking 10% of the moles. So we go from 0.20 moles to 0.02 moles. And so when I take the moles and divide it by liters, I wind up with the exact same molarity as before, which isn't surprising because both of these numbers went down by the same factor. So a very important point. The aliquot has the same molarity as the original solution, and you should write that down. Okay, after the aliquot is taken, the dilution occurs. The solution is diluted to 5 liters. We still have the same amount of moles of NaCl, but they're now swimming in a much bigger volume. So this is where our molarity finally changes, as we'd expect from a dilution, and we get 0.02 moles divided by 5 liters equals 0.004 moles per liter. So the molarity has gone down by quite a bit, which makes sense because we've diluted it by quite a bit. And so I now have a few questions for you. And they all relate to one big question. Why go through all this process? Is this just like a textbook problem to see if you can solve an analytical chemistry dimensional analysis problem? Or is there a practical reason for this kind of effort? And of course there's a practical reason. So ask yourselves these 3 questions. 1, why dilute the solution at all? Why dilute? Wait, why am I doing this when I can just do this? Why dilute the solution at all? Why not just work with the original solution? This is actually the trickiest of my 3 questions, and don't bother writing it down. I'm not. Just think about it. Question 2. If we're going to do a dilution, why not just dilute the original solution? Why go through the effort of taking an aliquot and diluting that instead? There's actually a couple of answers to that question. And question 3, if we're going to dilute that smaller volume aliquot, why even make the bigger solution in the first place? Why not just make that smaller volume with a lower amount of NaCl from the get-go? In other words, why weigh out this larger amount of NaCl and then dissolve in 1 liter when we could have just weighed out this smaller amount of NaCl and dissolved in our 0.1 liters? Usually I would answer these questions in the video, but I'm actually going to wait till Zoom to answer this, so leave some space in your notes. That's because when we do these lectures live, I like to really address the class with these questions and see what they come up with. So for now, just think about it, again, leave some space or write it in later.